do is I want to talk about the direction of the electric field. Okay, look at this formula right here. I'm going to look at this formula to determine the direction of the electric field. Okay? Notice these equipotential lines, right? Equipotential lines means that that difference is what? Zero. Okay? Because they're equipotential lines. Okay? Now I do vaguely remember going over this last Wednesday a little bit, but I want to hit it a little bit harder. Now that I feel a little better. Hit this home, okay? That's zero. So the only way to make this zero, there's two ways to do it. One is to not move. Okay? One is to not move. The other is to have the electric field be zero. Well, neither of those work. If I've got two voltages here, the electric field is, and not moving, it doesn't do anything for me. It doesn't do anything for me. So how else could I make this zero if neither of those are zero?
If you're moving along one of the lines. So
it's the other way. It's the other way. Because it's dot product, if I'm moving along one of the lines,
like a 40-volt line.
Yeah, if my DL is parallel to E, oh, you mean one of those lines, right? Okay.
Yeah.
If my DL is parallel to E, right, then of course, there's going to be this is not going to be zero, because this is not zero and this is zero. How would I make this zero? To go along an equipotential. In other words, when I'm moving along an equipotential line, I'm moving like this along an equipotential line, right? That's my DL, okay? How do I make my dot product zero here? Go ahead.
I forgot whether it was dot product or cross product, but it has to be perpendicular.
If E is perpendicular to DL. So what that means is that the electric field here is always going to be perpendicular to the equipotential line. Always. Always. So my electric field must point perpendicular to it. And so for these equipotential lines, if I were to draw my electric field lines, I want to make sure that at each crossing it's perpendicular. That's not really perpendicular, but I'm saying it is, so perpendicular. If I were to draw it out here, notice it would go like this. See, it has to go out here like this. It has to bend here so it can be perpendicular. Bend here so it can be perpendicular, and then come out perpendicular like that. There was a laboratory that, how many of you are in 220B lab right now? There was a laboratory that we once did called electric field mapping. Do you still do it? Did you do it? You should have done it by now. No, okay. Well, what you would do is you would actually find these equipotential lines by using a little voltmeter to go around and find lines of equipotential. You'd put the dot on here so you'd have one be zero. And then you'd look around here, where's the 50? Where's the 40? Where's the 30? And then you draw these equipotential lines, and then one of the things you wanted to do is to draw the electric field lines. And the electric field lines are always going to be perpendicular to it. It's not there anymore.
It's this week.
It's this week.
Electric field plotting.
Oh.
250.
Why would it be this week?
So right after the midterm.
Yes, where you have this. Well, anyway, well, at least your lab will be easier. You'll know what to look for. Okay. Now you might use it. The other way to do it is to use what they call a galvanometer to find points of equipotential, and that we won't get to in here how that kind of thing works until next week. What a galvanometer does is if there's lines of equipotential, you'll learn it pretty soon. If my two endpoints have equal electric potential, no current will flow. Because why on earth it wouldn't flow? It's kind of like a flat. If the table's flat, water's not going to flow. Okay? So think of it that way. So you guys might have gone over current first, and then you're going to do this with the galvanometer. Okay, all right, now let's get to the problem itself. Now that you have those two concepts in hand, let's get to the problem and see how that question is answered. Okay? All right, so it says a proton is released from point A. Indicate the direction of the electric force vector acting on the proton. Now, so point A here. So first of all, the electric field is going to point from high to low voltage. And it's got to be perpendicular to this line here. So perpendicular would be which way? To the left. So the electric field is going to be pointed to the left. Points from higher to lower voltage and perpendicular to that line. So it would be to the left on this paper. Okay? To the left.
The
So
higher to lower is because it's positive, right? This is a
the higher to lower is one other thing in this formula that I give you, which is why I like my formula better than the book's formula, because I go initial, final, final minus initial, and I integrate from initial to final, which is what you think you would do, you should do. See that minus sign? That means the electric field goes from high voltage to low voltage. High voltage to low voltage. Okay? That also is consistent with the fact that electric field goes from positive charges to negative charges. Positive charges create positive voltage. Negative charges create negative voltage. So it's all self-consistent. All of our rules are self-consistent. They have to be. If we ended up with a contradiction somewhere, we'd be like, it'd mess it all up. Some other weird charge that doesn't have a plus or minus sign, it would be a different charge. Which, by the way, is why it's so confusing when you talk about the force between quarks instead of these things, because quarks have 3 different types of charge they could have. And we call them colors, even though they're not colored at all, but we just kind of call it colors. That's a fun part of physics that if you guys go into that field, man, I love it. So you see me, I'll congratulate you. Okay. Well, anyway, let's go back. Okay, so in this case, we want it to be to the left. Okay, so the answer here is to the left. Points to the left. There it is. Whoops, I forgot to extend that because there's one other thing I need to say. The electric field points to the left. Okay. Now it's a proton. We have to use that last formula, so it will be moving along the electric field to the left. An electron is placed at point B, indicates the direction of the force vector acting on the electron. So now the electron's at point B. The electric field is going to point from high voltage to low voltage. High voltage to low voltage has to be perpendicular to that. So what is the direction of the electric field? Electric field.
to the left.
To the left. But because it's an electron, it's going to move to the right. Yes?
Wait, does this mean electricity flows backwards through circuits?
Yes, but don't tell anybody.
Okay.
Because the physics is the same. Yes? It would move to the left. Positive charges move along the electric field. Negative charges, the forces against the electric field. Okay? And that comes from this formula right here. Because you see, it's a vector formula. You know, this has a direction. This is just a number, so it's a magnitude. If that magnitude is positive, then it will be in the same direction. If the magnitude is negative, if that Q is negative, sorry, magnitude is negative. If the Q is negative, then it will be, these two will be in opposite directions. Okay, so, I didn't submit these, I'm sorry, let me submit. Because you gotta remember, you always must submit to mastering physics. Submit to the master. An electron is released from point B and a second electron is released from point C. What can you say about the electric forces experienced by these electrons the instant they are released? Okay? So now it doesn't mean later of this release, it means the instant they're released. Okay, so let's see. Both of them are electrons, and we said that the electron force at B is going to move to the right. Okay? Let's take a look at the direction of the electron force at C. Electron force at C. It's going to be in which direction?
Up.
It's up. Okay? High to low, perpendicular to this. It's an electron, so you go the other way. So the electronic force is up. All right, so, it talks about greater or less force. Well, greater or less force, since they both have the same charge, in order to get more force, I need more electric field. Okay. Once again, going back to this formula here, this formula right here. that formula right there. Okay? The force, same charge, I need a greater electric field. So really what they're asking is which one of these has the greater electric field? Which one of those 2 points has the greater electric field? And let me find it.
C.
Oh, yeah, there we go. Strong thing. And C, because you notice that these 2 lines are closer than these 2 lines. Okay? So these 2 lines are closer, so C is going to have the greater force. So, okay? C
Will
is.
this test have questions?
Oh, I love questions like that. There will be conceptual questions, yes. I need you guys to have some conceptual questions too. Okay? Sometimes I might mix the conceptual questions in a problem. The other time I might have a conceptual questions that are separate, multiple choice type questions, you know, at the end, or short, you know, problems, you know, short calculations. Yes, sir.
For part C, are we assuming that A is not there at all?
Oh no, it just says there's an electron at point B and at point C.
Okay.
So they don't talk about A.
All right.
By the
I
way,
was assuming that A was there. And
if A was there, then A would have the greater force than either of the other 2.
But wouldn't A be interfering with B, and that would help to make
No. Because we're assuming that these voltages are created by a lot more charge than an electron and a proton. Okay, so we're not considering anything else we've put. Okay, so that just says this may work. Now, I guess when they got close enough here, they started doing it. But even if you had something at A, all right.
Why?
Go ahead.
So why does C experience a greater force?
Because these lines are closer together. That means there's a greater electric field. A greater electric field. All right, let's look at another one. That was a good one to go over. All right. Any other these ones trip you up? Which one?
They have like 2 shells, I think, and each side.
2 shells.
We change the center.
2325. 2 shells. 2 shells. It looks like this. Blah, 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 blah. This one?
Yes.
A thin spherical shell of radius r equals 1 centimeter is connected with both shells are made of insulating material. The smaller charge is 6 nanometers. Blah 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 blah. Do not worry about this problem.
Oh, sweet.
Do not worry about this problem. Okay. This involves integrating back over the electric field. So you'd have to calculate the electric field using Gaussian law. That I still would like you to be able to do with something like this. But what I don't want you to have to do is to integrate to get because we never actually did, you know, simple things, not complicated things like this. In fact, hang on, let me do something for you. Hold on. Assignment, outcome, where is that one? Okay, so let's make it, well, how many of you did it? Did anybody like to do it? Fine. I do this for my 100 class too, by the way. If there's a problem on there that I might, oops, that one in. That's that 2 points of extra credit for you guys is for putting up with me being sick last week because I couldn't go over that because I was sick. So you guys win. You win. All right, how about another one of these? You want to look at another one?
Professor?
Yes.
The second problem of the list.
This
part
one?
C, yeah.
Part C. Let me see about part C here. Okay, so their total electric charge of 2 nanocoulombs is distributed uniformly over the surface of a metal sphere with a radius of 20 centimeters. The potential at 0 is infinity. Okay, so then what it tells you is it talks about, no, not this one either.
No?
Well, wait, it's a metal sphere? Okay, you can do this one, and I will show you how. I will show you how to do this one. Conceptually. Okay?
I just wonder why.
In other words, hold on. If you're integrating here, you're doing too much work. Okay? If you integrate here, you're doing too much work. And I'll explain to you in a minute what's happening. Okay? Because I have a feeling I know what your question is. So let me go over the problem. And then if I'm right about what your question is, then All right, here we go. So I have a metal sphere. It's a metal sphere, right?
Yeah.
Yeah, okay. Metal sphere. Okay. If it was an insulating sphere and they did this to you, I'd have to take it out. Metal spheres I could deal with. Okay, so there's a metal sphere. It's got 2 nanocoulombs on it. Positive? Okay, I'm assuming it's positive. So I got Q equals 2 nanocoulombs. And it's a radius of 20 centimeters. So I'll write that over here. Let me go ahead and show you what I'm writing here. 20 centimeters, which I will immediately change to 0.2 meters, okay? That's a pretty big sphere, but there it is, okay? And we're told that the potential at infinity is 0, okay? The potential at infinity is 0 for any theoretical charge distribution that you have. Like if I have a line charge and I want to calculate the voltage from a line charge, if I have a point charge or any type of charge, the standard is to take the V at infinity is 0, away from everything in the universe. So away from everything in the universe is 0. Okay, now normally I think, well, oh my goodness, I have to integrate this because I want to find out what the voltage is at 45 centimeters. So I want to find out the voltage at, let me change my variables here. There, I need that. Because I'm going to use little r as my varying radius. My capital R is my radius like that, okay? Okay, so I want the voltage at 45 centimeters. Now, if I'm at R equals 0.45 meters, where am I in terms of those fields? I'm outside of it. Outside of it. Outside of any sphere, any spherically symmetric charge distribution, what's it look like? It looks like a point. So if the electric field looks like a point, and you derive the electric field from the voltage from the electric field, right? Then the voltage is going to look like a point. It's going to look like a point charge. So anytime I'm outside of a sphere, I'm like, oh, fine, I'll even use the one that I had to give you because they gave it to you. So I look on my formula sheet, and I look down here. Oh, there it is. 1 over 4 pi epsilon naught Q over R. That's my voltage from a point charge. So 1 over 4 pi epsilon naught Q over R, where Q is the charge and R is how far away I am from it. So that's PAC here. So if I PAC, I got 9 times 10 to the 9. This is classroom plug and chug. You would use 8.988. In the classroom, we just round it off to 9. It's also was easier to remember too. 9 times 10 to the 9. All right, so and times Q, which is 2 nanocoulombs. What's nano? Negative 9 divided by my R, which is, whoops, not that R, this R, 0.45. Okay? So what do you get? Yeah. Well, like it did, it's 18 divided by 0.45, whatever that is. Because those factors have 10 to the 9th and 10 to the negative 9th conveniently multiplied, give you 1. Anybody get 40?
Yes.
Yeah.
Okay. All right, what are the units of that? Volts. Hopefully that one you could remember, Voltage has units of volts, okay? All right, so now we want to look at R equals 20 centimeters. R equals 20 centimeters. Okay, now right at the surface, okay? As long as we are just outside of the surface, which I have to assume we are here, okay? Just outside the surface, it still looks like what? A point. Still looks like a point. So we do it again. Okay, I'm going to take a shortcut here. This would be 18 divided by 0.2. I've already multiplied the charge and this, and I got this. 18 times 5? 90. There we go. 90 volts. This is where you have the question, right? Yeah, the question's coming up. Okay. Now we want V at, what was it? 11 centimeters. Actually, I don't care what it is. R equals 0.11 meters. Now we are inside the metal sphere. Inside the metal sphere. So in other words, at the surface of this metal sphere, the voltage is equal to 90. We calculated it because it looks like a point charge. Okay? Now we're inside the metal sphere. Let me go anywhere inside the metal sphere. I don't care. Let me go anywhere. Okay? Put that point charge put it right there. If I go from the surface along a DL inside the metal sphere, the sphere is metal. Any conductor, if the charges are allowed to rest, to move and rest, what's the electric field in there? 0. The electric field is 0 inside the conductor. So since the electric field is 0 inside of here, I don't care. VB minus VA equals an integral of a bunch of zeros, dots, other weird stuff, okay, that I don't care about, and negative 0. What do you get? 0. Which means that anywhere inside of the sphere, the voltage between any 2 points does not change, will be the same. The other way to look at it is, let's look at it in terms of that derivative formula. That derivative formula, which technically is the partial derivative formula, but we can just look at it as a derivative formula. So E in the x direction is equal to, and this could work for anything. This works for anything, right? So minus dV dx. If electric field is equal to 0, if the derivative of something is equal to 0, what is that something?
Constant.
A constant. So the entire metal sphere is at the same voltage. The entire metal sphere is at the same voltage. The whole sphere as it equals 90 volts. All of it. Okay? The whole sphere. So it's still 90 volts. Okay? So conductors E equals 0 inside. Voltage is constant inside. It's a corollary there. All right, now let's take a couple minutes and try to look at a couple things from chapter 22. Oh, whoops. Gaussian fun. Wait, what happened? Oh, there it is. Okay, stay. All right, so which one would you like to see me do with this one here? want a high concept one?
Yes.
Sure.
High concept, right here. Flux through a cube. Oh no, that's integration. That's not high concept. Darn. Yeah, let's not worry about that. I don't want you guys to get too confused with worry about integration, okay? 19? Okay, let's see what this one does for us. Okay, a hollow conducting sphere with an outer radius of 0.26 meters and an inner radius of 0.2 meters has a uniform surface charge density of 6.67 times 10 to the negative 6 coulombs per meter cubed. Meters squared. All right, so we have a hollow conducting sphere, has an inner radius and an outer radius. Okay, and it has a charge density of 6.67 times 10 to the negative 6 coulombs per meter cubed. Meter square, sorry. And we're going to end up sticking a charge inside of it, Q. Q is equal to negative 0.8 microcoulombs. Okay, so, and we have an inner radius of 0.2 meters and an outer radius of 0.26 meters. Okay, so then it asks us some questions, okay? So in other words, that sigma is an excess charge that was put onto that sphere. An excess charge that was put onto that sphere. I have a bit of a problem with the way that they worded it because it seems to me that you would have to be known where the charge was in the first place to find out the total excess charge on the sphere, not just the excess sigma, okay? So, if this charge is on the sphere without this one, where is it? In other words, here, let me draw the shell without the shell without the charge. Okay, so I just have a shell, and there's no charge in the middle here, and I put charges on this. Where are they going to be?
Uniform.
They're going to be on the shell, on the outside of the outer shell. That's where they're going to be. So I'm going to throw this problem out, just to let you know, because I don't like the fact that you're not told which one it is. I can figure out the inner charge density shell regardless, though, because I can always figure out how much of that charge is in here. But they need to tell you what the charge is unless they tell you specifically it's on the outer shell. It just says it's there, it says that's the charge density on it, surface. So I would assume it's the outside surface. Okay, you have to assume it's the outside surface. So let's figure out how much charge is there. So Q is equal to that surface charge density multiplied by the area. That's the total charge that's on the thing. That's the total excess charge on that shell. I'll call it QS shell. So you multiply 6.67 times 10 to the negative 6, multiplied by the area of the shell, the outer shell, which is pi, times 0.26 squared. Huge. Say so QS. So what you get for QS? Yes? Oh, it should be. Grazie. Hold on, that was a short circuit here. Let me help my circuitry.
Is that
That's better.
4 pi?
Yeah, because it's a sphere, not a circle. It's a sphere.
That 4 is in front of the pi, it's not a power, right?
No, it's not a power. The 4 is 4 is there. See, it's supposed to be. Yes,
Squeeze 4 between.
yeah. Let me squeeze a 4 between them. 4 pi there. That's 4 there. You wouldn't have something to the 4 pi power. At least I hope. Well, you would if you're working with complex numerals, but we're not. So, no.
5.67 times 10 to the negative 6.
Okay. Is that fine? 5.67 times 10 to the negative 6? Yeah, because it's 4 pi. Okay, 5.67 times 10 to the negative 6. Coulombs, or 5.67 microcoulombs, okay? So now to what I would expect you to do, okay? Given this charge on the shell and given the other charge in the cavity, okay? I would expect you to be able to figure out where the charges are in this distribution here, where the charges are, by using the principles involved with Gauss's law. Principles involved with Gauss's law. So here's the way the principles work. So let me draw the shell. And now I stick this charge in the middle. Negative 0.8 microcoulombs. So when I do this, because that is a conducting shell, how much charge must be in here?
Positive 0.8.
Positive 0.8. Must be. Because remember, if you do the Gauss's law inside of the sphere, the charge contained inside of that must be 0. Must be 0. So, this charge must be positive 0.8 microcoulombs.
That's the inner shell, right?
That's the inner shell.
Surface.
Right. Now the thing is that how much charge did I have on the shell? Positive what? 5.67. Does that mean I don't have enough to do this? Well, the answer is obviously no, or they wouldn't give you this problem at all. It wouldn't make any sense, right? You got to remember that in any kind of metal, you've got plenty of positive and negative charges to go around. So if I need extra positive charges, sure, I got plenty of them. All that means is there's going to be now an excess negative charge that has to go to the outside. So in other words, because the charge before, whatever charge is on the inside plus the charge on the outside must equal the original charge of the shell to begin with, because of conservation of charge. When I put that charge on the shell, it has to go somewhere. Charge still is conserved. So now I can figure out the charge on the outside of the shell by taking this and putting, I've got on the inside of the shell is positive 0.8. On the outside, that's what I'm trying to find. I'm trying to find Clout. 5.67 microcoulombs. Whoops. Oh, I've got plenty, I'm sorry. That's 5, not 0.5. Oh, well. That was 5, right? Not 0.5?
Right.
Oh, okay. All right. So my outside is, take this off of here, and you have 4.87 microcoulombs. Yes?
So it's only the edges of the shell that have any charge, everything in the center of the shell?
There's no excess charge in the center, right. And the reason why is because there's no electric field inside of there. And those charges can move. And if they try to move at all, they're going to try to get away from each other. Let me just go over the electric fields, the electric fields about this particular problem here. The electric field inside of here looks like what? The point charge at the middle. Because remember, when you draw your Gaussian surface, as long as it's spherically symmetric, you draw your Gaussian surface inside of here, you're only going to see that charge. You're not going to see the shell. If the Earth were hollow, let's say the Earth had equal mass as it does today, and it were hollow. By the way, there's a channel called, I think this one was on Vsauce. I don't know if anybody ever does the Vsauce. It talks, he asked about what if the Earth were hollow. I think that was one of his. Not sure, but if it's not, just that what if the Earth were hollow? What would happen is, on the surface of the Earth, we would feel the same amount of gravity because we're outside the Earth's surface. So I don't care any spherical distribution, whether it's hollow, whether it's solid or whatever, you feel the same thing. Because outside of here, it looks like a point charge. Okay? But if you go inside of the Earth, the hollow Earth, right? Inside the hollow Earth. Okay? Well, if you go inside of the regular Earth, what you do is you feel the charge, you feel the mass below you. That's right, you feel the gravity from only the mass below you. That's the way Gauss's law works, because it's only what's enclosed inside of that sphere. Because all those other masses end up canceling each other out, which is why Gauss's law is so cool. I don't have to integrate over the dumb sphere to figure this out. To figure out that these masses that I might not understand cancel each other out do. They actually do, because of the nice spherical symmetry of the Earth. Okay? But if the Earth is hollow and all its mass were on the surface, you dig down in there, you're only feeling the gravity from what's underneath of you. What's underneath of you? Nothing. Whee. Pretty, huh? Now, there are other nasty effects that happen because of that, so we wouldn't really want our Earth to be hollow, but that's what would happen here. Yes?
Do you feel a little bit of centrifugal force?
From the spinning part?
Yeah, just a small amount.
I'm trying to think if that would. I haven't thought about that. I haven't really thought about that at all. I might actually ask Vsauce, would you still feel the centripetal force? Because if you're inside, there's no gravity. Earth is, no, because the gravitational force. Now, but because the Earth is spinning, if you went in there, you would still be spinning with the Earth. Oh, that's weird. So, yeah, because.
Kind of similar in movie The Martian. where they have the ship spinning so
Yeah,
they
they have
can
the ship
feel
spinning to simulate the
gravity.
gravity, yeah. That's like, yeah. Anyway, no, I haven't thought about that. That's a good question. All right, so outside here. What about inside the conductor? E-field is? Thank you. Outside of all of this, what does it look like? A point charge of everything that is inside. So this plus this plus this. In this case, with a hollow shell up here, with this shell, it becomes easy because these two things cancel each other out, and all you have is this. Okay? Yes?
So the green shaded part between the two radiuses, is that where the 4.87 maximum lies, or
The 4.87 is on the outside of that green shell. The 0.8 microcoulombs is on the inside of that shell.
So what's between 0.8 and
Nothing. There's no charges in there. That's electrically neutral conductor inside of it. Yes?
So we feel if we were outside the show, we feel QS or Q out?
The Q out, actually. Because the QS is what was on the shell. It's what's on the shell itself. But we stuck that other charge in the middle. So we feel the whole effect of all the charges there. Okay, let me go ahead and take a look at your formula sheets here.
Professor, are we allowed to write on this sheet?
I'm debating about it. There's a reason why I don't want to, and that's so I can give you easier problems. If not, what I have to do is I have to make the problems more complicated because everybody will be trying to, like, memorize it. Then I have to make the problems complicated to make sure you understand what's on the formula sheet. Okay. There is one thing I did not put on the formula sheet here, and it's another thing that you have, that you get bonus from me because I was sick last week. Okay. Remember when we had the DE formula, the D electric field formula that I used to D electric field, where we had you had to put the DQ in and the R and the R hat and all that stuff. That is not going to be on your test. Do not have to integrate over finite amounts of charges. One thing that I do want you to be able to do, okay? Now there are integrals on your test, but they look kind of like this. That's Gauss's law. And remember, we never actually had to do the integrations for Gauss's law. Or they're going to look like this, where I'd have to either make this simple enough for you to integrate over, kind of tell you what it is, or give it to you maybe in this form where you can take the derivative instead. Okay, so I don't want anything really complicated in terms of your integration. Okay? It's not that I won't put integration conceptually on there. I just don't want it to be an issue because that is something that you really need time to do. Okay? And I'll also do you a favor for the future tests too. Okay? If less than 50% of you blow off the integration problems on your homework, I won't put it on a future test either. The problems where you actually have to integrate something. Okay? But I don't want you blowing it off because it's not on the test. Okay? I want you to learn how to do it. Okay? But I don't want that to bog you down in terms of the concepts and the understanding. Because how many of you are in electrical engineering or something with electrical engineering? How many of you in here are there? I apologize to the 1, 2, anybody else? Where are the rest of you? 3, 4, 5, 6, 7, 8, 9 of you. I apologize to the 9 of you, okay? Because you, unfortunately, will see these integrals and things again, because you guys have to take EE 370, right? 370, the Fields and Waves class. And that class apparently is the one for which the theoretical part of this course really comes into play. So make sure you guys, pick that integration stuff up. Even though, just try to do the best you can. And I will be going over it in lecture. And I will expect it on the homeworks. Don't blow it off. Ready? No, I should be, I'm sorry. 75% there. 75% you must at least make valid attempts at this integration. I'll probably stick it on team problems and things like that so you guys can. There is one thing I will expect you to do in terms of things like finite line charges, right? Here's something I expect you to do. Let's say that I have a line charge, and let's say I put a charge on it of let's do the yeah, I should do nanocoulombs just to make it so it's not so ridiculous. So I'm going to put 5 nanocoulombs of charge on this thing, and it's a line of charge, and it is and it has a length of, so the length of this is I don't know, 0.20 meters. Okay. Okay, 0.2 meters. Okay. Okay, I'm going to be looking at the electric field along the x-axis here. Along the x-axis here. This is why I don't want you to write a bunch of other stuff on your sheets. That's why I'm just, because I want you to be able to think about this instead of writing down a formula. That. Because yes, they actually derived this in your book. They actually derived this in your book. But you don't need that for the questions I'm going to ask you. That's why, so that's the way I can give you this kind of problem and you ask. Because I promise you, I'm not going to make you integrate. You write your integral down for this, you're doing, Okay? What I want you to be able to do is 2 things. A, estimate the electric field at x equals 0.003 meters. And I might even give you a hint. Here, x is much, much less than L. Now, I want you to look at the formula sheet that you have. And I want you to look at the picture. And I want you to tell me, if I'm really, really close to this thing, what is it going to look like?
Infinitely long.
It's
chart.
going to look like an infinitely long line. There you go. So all I have to do is use the infinitely long line of charge formula. Which one is it? I gave you 3. See, I see it. Which one is it?
K lambda over R.
The K lambda over 2R, okay? So the 1 over 4 pi epsilon naught. So it's 1 over 2 pi epsilon naught. So I use the long line of charge. So would be this, K lambda over 2 pi R. Or 2 pi R. Oh, I hate using K. I'll just use K. I'll just use this. 1 over 2 pi epsilon naught lambda over R. If I put it in terms of K, that is K lambda over 2R.
Isn't
Right?
K 1 over 4 pi epsilon?
Yes, that's why there's has to be a K lambda is 1 over 4 pi. So it's this. Yeah, if you put it in terms of the K. I gave that to you up here. Okay, this, and I also gave you epsilon naught itself. And the only reason why I gave you these formulas instead of the formulas with K's in them is because these are the ones that are in the textbook. They gave me. Okay. I just did this so I could calculate it easier.
So are we bringing this paper to the test, or will they?
I'm going to give you another paper just like this at the test. Okay?
You can write on this one.
You can write on that one all you want to for studying purposes. So you have reasons to memorize. Okay? Okay? So, so it's 2, 9 times 10 to the 9th. How do I calculate lambda here? Q over L. So I've got 5 nanocoulombs divided by 0.20 meters. Now, sometimes, and I'll let you get away with this too. Sometimes if there's only 1 nano in your thing, or 1 micro in your thing, or one of those factors, just carry it along, especially if it's in the numerator here. Because all this is 10 to the negative 9. Now if I plug 10 to the negative 9 in the calculator and divide by 0.2, blah, 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 I'm still going to get 10 to the negative 9. Okay, come on. You see what I mean? So this is just 10 nanocoulombs per meter. Okay, everybody see that? I'll just carry that nano. 5 divided by 0.2. Let's just use by nanocoulombs for now. So I'm going to put that in here. So that's 10 times 10 to the negative 9. Divided by the radius r, which is 0.003. All right, somebody calculate this and tell me what the electric field is. Conveniently, these factors of 10 to the 9 and 10 to the negative 9 cancel out. Ha ha ha. So it's 2 times 9 times 10 divided by 0.003. $60,000? Everybody get 60,000 on this? Okay. Units here are newtons per coulomb. Okay. Now here's part B. Estimate the electric field at x equals 30 meters. 30 meters. Hint. Shall I give you the hint? Do you know what the hint is here? You see where this is going?
Treat it as a point charge.
Yeah. Hint. The x here is much, much bigger than the length L. So if I get really close to this thing, and this is what I want you to be able to do, visualize stuff like this. If I get really close to that, it looks like an infinite line. If I get really far away from it, what's it look like? A point charge. E equals, and I can it's KQ over R squared. There you go. That's what it's going to look like. Nine times 10 to the 9. 5 times 10 to the negative 9 divided by 30 squared. Somebody do that and tell me what the electric field is. Far, far away from the thing. 0.05? So if I give you these estimate questions, I will pick distances that are obviously either really close to what's going on or really far away. Because you want to be able to visualize those type of things. When you get close to something, it looks like it can look infinite. When you're far away from it, it's going to look like a point. Okay? If there is a formula that you wish to request be added to this sheet, please feel free to ask. I will try to have something up for you in terms of a sample that you can go through. And I am going to be posting the solution to the second team problem. Not the first team problem because it involved integration, or sort of integration, but that's a bit complicated. The second team problem. Yes. Yes, the one that you turned in when yes. I'm going to try to post a sample on Google, or like an old test that I gave. I got a couple of other announcements if you're leaving. If you're with DRES, just come see me. I will, send those things over. And if you're forgot. Anyway, you got questions to come up. Okay. It's the type of problems. I'm trying to get used to the type of problems, which is why I started asking some of these, because those problems that are conceptual in nature, where it looks like, oh my. Let me go ahead and hand out the gifts. Okay, the gifts for you. Okay, so I have a gift for each of you. Come up and get one for your friends. One for you and one for your friends that are in this room. So I'll just lay them in several different places and you can come get them. Okay? Here on this table that for some reason they keep putting back over here. I know they're probably like, this is over here for? Here, and I'll put some of them on this chair, and I'll push that chair over there. And I better take one for myself so I can remember what all I said.
Oh, thank you.
Did they run out of chairs? You can put those on the chair. Put those on the chair. They already got theirs. Okay, so today what we're going to do is we are actually going to review for your midterm, which is on Wednesday. Your first exam is on Wednesday. It covers chapters 21, 22, and 23. Though because of all the stuff that's happened, there are some things that I will not test you on, and I want to go over that a little bit after we talk about a couple of problems that are here. I'm going to start with chapter 23. But if anybody has, after we get through with like maybe a couple questions on chapter 23 homework, I'm going to go back and pick up chapter 22 because I didn't get to discuss chapter 22 homework with you guys because that was the day I was out. That would have happened. And had I had the substitute, I would have actually gone over chapter 22 with you on Wednesday, but I couldn't because I had to cover chapter 23. Okay? So what you'll find, and if there are any problems on this chapter that involve integration, I will eliminate them from the homework. So you don't have to worry about asking about those particular problems, just to let you know. Okay? Because I didn't get to go over integration in terms of voltages. It's actually a little simpler than the other ones, but you know, I didn't get to go over it, so. So are there any of these you'd like to see me work?
Wait, for this, I think it's the relationship between electric force.
This one here,
I think
potential.
it's one of those, either of those two conceptual questions.
Okay,
But
so
it was
so
really-
you want to see these conceptual ones?
Sure.
All right, relationship between electric force.
Oh, it was this one.
This one here, okay. All right. The relationship between electric force and electric potential conceptual question, okay? 3 points A, B, and C are shown. So you show A, B, and C, okay? A proton is released from point A. Indicate the direction of the electric force vector acting on the proton. Okay, so what we have to do is we have to go back and refer to the equation. And so I'll show you how to do it. So let's go back over here. So the relationship between electric force and electric force and electric potential. Okay, electric force and electric potential. Well, what they're doing is we're using two equations here. First of all, the one with the we relate the electric field to the potential, and there are two equations for this. There's this one here, VB minus VA equals minus the integral from A to B of E dot dl. Okay, E dot dl. Okay, and then there's, after we get that one, there's this one. F equals Q E. Okay, first of all, let's try to simplify this first equation here. We also have this one here, the other form of it, where we have E in the x direction is equal to minus partial derivative of the voltage with respect to x. If you have to use this particular equation, I will only have x dependence. Okay? I will only have x dependence. That way you could turn the partial derivative into a regular derivative, and everybody knows how to deal with that. Okay? Or that's Calc 1. Okay? So now let's tackle this conceptually here. Let's tackle this conceptually here. And I'm actually going to look at this equation first, and then this equation, to tackle this conceptually as to what's going on. Okay, first of all, if we look at this equation here, if I have these equipotential lines, okay, so like, let's take a look at this equipotential lines. Let's say I do this, right? I have 60 volts, 50 volts, 40 volts, 30 volts, 20 volts, okay? Okay, 60 volts, 50 volts, 30 volts, something like this, okay? And now if I were to ask, if we want to take a look at this equation here, let's simplify it. Let's simplify it. Instead of saying that this is some kind of continuous thing, let's say that the voltage or the electric field is constant throughout there. In other words, instead of it being some kind of electric field that's like varying like normal, that's where you get this. If this is a constant electric field, then what we can do is we can change these D's here to deltas. In other words, if we're looking for the average electric field. So we're going way, way, way back. Remember when your first equation was the average velocity and you used deltas instead of the derivatives? Way back when. Well, that's what I'm going to do with this, because that's conceptually easier to understand what's going on. It's like this. So the electric field is equal to minus delta V over delta X. I'll go ahead and use delta X. Okay? That's the average electric field. Okay? Now, what's that tell you? Is that it's between any 2 points. Between any 2 points. If the delta V is the same between those 2 points, then the closer those lines are together, the greater the electric field. If you think of it like a topographical map, so let me go back to the topographical map idea. If I have lines on a mountain like this, the lines of equal height. Okay, if you look at something like this, you know, okay, something like that, okay? What would you say about these lines, topographical lines, where they're closer together?
Steep.
It's steeper, okay? So in other words, that's greater. That's greater flow. So it's like this. So in other words, you can think of the electric field as being the steepness when you're looking at an equal potential. When you're looking at equal potential, okay? So it's kind of like the steepness here. All right, so here's that. So one thing that I get from this is that right in the center here, the electric field is going to be larger than it would be out to the sides. Because if I extend these lines out to the sides, notice that this line is going to go like this. So my delta V between here and here is going to be the same. So the electric field here is going to be larger than the electric field here. So let me just call this point A and point capital A. Okay, capital A and capital B right there, like that. Okay? So A and B. So the electric field at point A will be greater than the electric field at point B. Okay? So does everybody see how that works with the magnitude of the electric field? The magnitude. Now we want to look at the direction of the electric field, the direction of it. Because that's another thing you're asked in this problem, conceptual problem. And by the way, I do love this conceptual problem. I love it. I love problems like this, okay? Because they're either you get it or you don't. I want you to get it, okay? I want you to get it. So you guys are going to get it. All right, so now what I want to